A famous Nobel laureate has warned that the James Webb Space Telescope has uncovered something unusual in the universe, and we may not be prepared for the changes that lie ahead. The latest discoveries are presenting profound challenges for our understanding of science, making the situation even more perplexing. The James Webb has detected an entirely new phenomenon that is turning our textbooks on physics upside down. Astrophysicist and Nobel Prize winner Adam Rees, who has long believed that mainstream scientific theories are headed for disaster, is now raising concerns. Reports continue to flood in about the growing number of inexplicable cosmic puzzles, and the big question is whether science can ever truly grasp the situation, or if our current understanding is coming to an end. Adam Rees, one of the leading experts in the study of the expanding universe, remains calm and thoughtful amid the whirlwind of revelations brought by the James Webb Space Telescope. Since its launch, the universe no longer seems as it once did. It may actually be much older than we had thought. Galaxies are forming much more quickly and in ways that defy all expectations. Additionally, the idea that the universe is expanding from a single point may no longer hold true. Recent findings suggest that dark matter itself could be a mistaken concept, and the James Webb is revealing new, puzzling images of the cosmos that challenge our fundamental assumptions. Rees is known for his groundbreaking work on the acceleration of the universe's expansion, a discovery that revolutionized our view of cosmology and helped establish the Hubble constant. He welcomed these new findings, knowing that his own work has already shown that our understanding of cosmology is flawed. Rees was instrumental in using supernovae as standard candles, a method for measuring distances in the universe, which provided extremely precise results. However, his team encountered a significant issue. They found that the universe's expansion was accelerating regionally, rather than uniformly, as was previously assumed. This discrepancy between measurements from Rees's team and those based on the redshift method marked the discovery of what became known as the Hubble tension. Their groundbreaking work led to Rees receiving the Nobel Prize in Physics in 2011, shared with his colleagues Saul Perlmutter and Brian P. Schmidt, for their work on the accelerating expansion of the universe. Rees and Schmidt were part of the High-Z supernova search team, which refined the method of measuring cosmic distances using supernovae. Meanwhile, Perlmutter's team made similar discoveries, using Type Ia supernovae as precise distance indicators, which revealed that the universe is not slowing down as expected, but speeding up. The result was shocking. The universe's expansion was accelerating due to forces other than gravity, as once believed. These findings sent shockwaves through cosmology, signaling a breakdown in the isotropic model, the assumption that the universe looks the same in all directions. This concept has been a cornerstone of modern cosmology, which states that, on a large scale, the universe is both homogeneous, uniform in structure, and isotropic, appears the same in all directions. Observations like the cosmic microwave background radiation once seemed to support this view, showing a consistent pattern across the sky. But now, this foundational idea is facing serious challenges. Recent data from the James Webb Space Telescope suggests that the universe may not be as isotropic as previously thought. The accelerating expansion that Rees and others discovered is not only surprising but also much faster than earlier models predicted, putting into question the very assumptions of traditional physics. This brings us to dark energy, a mysterious force believed to be responsible for the accelerated expansion of the universe. Its precise nature remains unclear, but it accounts for around 68% of the universe's energy content. Scientists have long relied on dark energy to explain the accelerated expansion, as it appears to counteract the effects of gravity. However, recent findings from the James Webb Telescope have begun to shake this understanding. The telescope's unprecedented ability to observe the early universe has revealed structures and objects that are much older and more advanced than expected, according to the standard model of cosmology. These findings suggest that our current understanding of dark energy may be deeply flawed, and they could ultimately lead to a dramatic shift in our perception of the universe itself. As the James Webb Telescope continues to unveil new mysteries, the world of astrophysics finds itself grappling with more questions than answers. What will these discoveries mean for our theories about the universe's origins and its ultimate fate? The future of cosmology is likely to be as unpredictable as the discoveries that the James Webb Telescope is revealing. From 2001 to 2010, the Wilkinson Microwave Anisotropy Probe, WMAP, played a crucial role in exploring evidence of the Big Bang by tracking variations in the cosmic microwave background, CMB. More recently, the Planck satellite provided one of the most precise maps of the CMB. However, scientists still debate how to interpret this data. While some argue it provides conclusive evidence for the Big Bang, others suggest it could indicate collisions with parallel universes or point to the existence of the multiverse. The pursuit of answers is not only about understanding cosmology and observing the sky but also about unraveling the very fabric of reality itself. As the James Webb Space Telescope, JWST, continues to reveal new insights into the early universe, scientists find themselves facing more questions than answers. These discoveries have prompted a significant reassessment of some of our most cherished theories and assumptions. One of the biggest mysteries is the nature of dark energy, which is believed to account for the accelerated expansion of the universe. Despite comprising nearly 70% of the universe's energy content, dark energy remains elusive, as its properties resist detection by traditional methods. The observations made by JWST have added further complexity by revealing structures in the early universe that appear older and more developed than expected under current models. This discrepancy raises questions about whether dark energy operates as originally hypothesized or if entirely new forces might be at play. Another challenge to cosmological understanding lies in the concept of isotropy, the idea that the universe should appear uniform in all directions on a large scale. This assumption has been supported by observations of the CMB's consistency, but recent findings suggest that there may be deviations from this uniformity. If confirmed, these deviations could indicate that the early universe was more complex and varied than previously thought, potentially requiring a major revision of our understanding of cosmic evolution. In the quest for answers, scientists are exploring both visible and microscopic realms. Nobel Laureate David Gross, known for his work in particle physics and string theory, advocates for investigating the microcosm to unlock the universe's deepest secrets. His research on asymptotic freedom and the behavior of particles at high energies offers valuable insights into the extreme conditions of the early universe following the Big Bang. Gross theories suggest that understanding the fundamental particles and forces at play during these formative moments could help reconcile the differences between quantum mechanics and classical cosmology. The CMB, a remnant of the Big Bang, serves as a vital window into the universe's early stages. Its faint, uniform glow provides clues about the universe's initial conditions and subsequent evolution. Satellites like Planck have mapped the CMB's variations with unprecedented precision, revealing the seeds of structure that eventually gave rise to galaxies, stars, and planets. However, interpreting these variations remains a challenge. They could point to fascinating phenomena such as cosmic inflation or interactions with parallel universes. The idea of a multiverse, an extension of theories like string theory and quantum mechanics, suggests the existence of multiple universes beyond our observable domain. These universes might operate under different physical laws or dimensions, potentially explaining anomalies seen in our own universe. While still speculative and difficult to test experimentally, the multiverse hypothesis is gaining traction among physicists as they grapple with cosmic mysteries that defy conventional explanations. The role of observational astronomy in shaping our understanding is increasingly critical. Advances in telescope technology, from ground-based observatories to space telescopes like Hubble and JWST, continue to expand our cosmic horizons. JWST's ability to peer deeper into space and further back in time than ever before holds the promise of uncovering more profound mysteries and potentially groundbreaking insights into the origins and evolution of our universe. Beyond theoretical and observational boundaries, the quest for answers extends into computational modeling and simulations. Supercomputers play a key role in testing cosmological theories against vast datasets and exploring complex scenarios that simulate the evolution of galaxies, the dynamics of dark matter, and the interplay of cosmic forces on astronomical scales. These simulations complement observational data, offering a synthetic view of the universe that can be compared to real-world observations to refine or validate theoretical models. The interdisciplinary nature of modern cosmology underscores the need for collaboration across various scientific fields. Astrophysicists, particle physicists, cosmologists, and mathematicians work together to integrate insights from diverse disciplines, bridging the gap between the microscopic world of particles and the macroscopic domain of galaxies. This collective effort is crucial in developing comprehensive theories that can explain the universe's structure and evolution over billions of years. As humanity's understanding of the universe expands, so too does our awareness of the limits of current knowledge. The uncertainties and anomalies revealed by recent observations challenge scientists to re-examine fundamental assumptions about the universe's composition, forces, and ultimate fate. While these challenges are daunting, they also present opportunities for breakthroughs that could revolutionize our understanding of existence itself. In conclusion, the ongoing exploration of the universe through advanced telescopes like the James Webb Space Telescope is pushing the boundaries of human knowledge. Each new discovery brings us closer to unraveling the mysteries of dark energy, the early universe, and the fundamental forces that shape our cosmic landscape. Despite the many uncertainties, the pursuit of answers continues, driven by the collective curiosity and dedication of scientists worldwide. The next chapters in cosmology promise to be as exciting as they are illuminating, offering glimpses into realms far beyond our reach and tantalizingly close to understanding. The universe might have expanded much faster or begun earlier than previously thought. These findings suggest that there are still many critical components and forces in the universe, such as dark matter and dark energy, that we have yet to fully understand. As a result, we may be on the verge of a major revision to the standard cosmological model, but we're not ready for that shift just yet. We can't propose new theories without clearer data on what's happening. Will we find the answers in the realm of physics? Our revolution in understanding will need to wait until the James Webb Space Telescope provides more images and scientists make even more groundbreaking discoveries. Only then will we be able to assemble a new cosmic picture, though that could take some time. In the meantime, researchers across the globe are searching for answers to the mysteries that are already available. One scientist, David Gross, embraces this crisis and views it as an opportunity. Gross, a Nobel Prize-winning theoretical physicist, believes the answers to the universe's greatest secrets are not hidden in the cosmos but within the microcosm. His work in solid-state physics and string theory has made him a leading figure in the quest to bridge gaps in our understanding. In 2004, he was awarded the Nobel Prize for his discovery of asymptotic freedom in the theory of strong interactions. This discovery was pivotal in explaining the behavior of quarks and gluons, the fundamental building blocks of protons and neutrons, which are central to the standard model of particle physics. Gross has long argued that the fundamental principles and patterns of the universe must have counterparts at the subatomic level. He helped develop key ideas about the early universe, which, shortly after the Big Bang, was devoid of stars and galaxies. Instead, it was a hot, primordial soup where particles moved freely through space, unable to form bonds. Before the Big Bang, there likely existed a kind of quantum state in which all structures were perfectly balanced, adding up to zero in terms of their physical properties. Following the Big Bang, these quantum fluctuations broke apart, sending charged particles and forces into a largely empty space. Over time, these particles formed stars, galaxies, planets, and eventually life on Earth. Is Gross correct in saying that these particles hold the answers to our questions? Likely yes. But how can we study the behavior of particles from 13.8 billion years ago? To do so, scientists turn to the cosmic microwave background (CMB) radiation, which provides a relatively accurate snapshot of the universe shortly after the Big Bang. This radiation has likely remained largely unchanged over the millennia. However, quantum physicists and traditional cosmologists still disagree on how to interpret this imprint of the universe's origin. Currently, there is a disconnect between quantum physics and classical cosmology. The findings from the realm of matter do not align with the principles of quantum mechanics, and the connecting thread between them remains elusive. David Gross believes that the missing link could lie in yet-to-be-discovered particles and forces. He has been at the forefront of efforts to bridge the gap between these two domains of physics. As a co-author of string theory and a proponent of the unification of quantum mechanics and general relativity, he has worked to close the divide between these scientific worlds. Gross's research into asymptotic freedom explains how particles behave at extremely high energies, which is crucial for understanding the early universe. When the universe was in its infancy, right after the Big Bang, energy levels were incredibly high, and Gross's theories may help explain some of the currently obscure aspects of the universe's expansion. However, string theory, as Gross proposes it, remains highly controversial, with many traditional physicists finding it too speculative. Despite the debate, Gross believes that the answers to the universe's most pressing questions lie in the quantum fluctuations within the CMB. The CMB permeates the entire universe, and its subtle variations provide vital clues about the universe's early conditions. The COBE Cosmic Background Explorer satellite, which operated from 1989 to 1993, was the first to detect tiny variations in the temperature of the CMB, revealing important information about the state of the universe just after the Big Bang.